Suppose you have index sets. I'm going to write down this example here, and we're going to write down as prove that for all sets like A, B1, B2, and the rest of the sets, we're going to stop at B sub n. So you have index sets. A union with the intersection of the index sets, I starts from 1, stop at n, is equal to the intersection of A union with each BI. I starts from 1 and stops at n. This is the generalization of distributed law. Of the distributed law. Very good. So how do we prove that? Let us begin. We need to show that left-hand side is a subset of right-hand side, and right-hand side is a subset of left-hand side. So proof. We need to show that, number 1, a union with the intersection of BI's, I start from 1 goes to n, is a subset of the intersection of each union. And also, number 2, your right-hand side is a subset of the left-hand side. So the intersection of A union BI's, I start from 1 to n, is a subset of A union intersection BI's. Okay, so let the fun begin. I'm going to use the definition to prove this. So to show number 1, we're going to take a random element and show that that element lands here. To prove 1, we take X in A union intersection BI. I start from 1 to n, and then we show that that X lands in the intersection A union BI's. I start from 1 and stop at n. Let's put a question mark here. This is what we try to prove. Very good. So by definition, let's begin. If X belongs to a union with another set, what's the meaning of that? X belongs to A, or X belongs to the intersection of BI's. I start from 1, goes to n. Very good. So since X belongs to A, X belongs to a union with any set. That common sense using the definition of the union. So X belongs to A union B1, X belongs to A union B2. We can continue this process. X belongs to a union with any set. Okay, so what's the meaning of that? X belongs to the first set and X belongs to the second set because of A. A is common in all of them. So X belongs to the intersection of A union B1, A union B2, and the rest of the intersections. So what's the meaning of that? It means that X belongs to the intersection of A union BI's. I start from 1, goes to N. We prove this. So far, so good. So this is the very first scenario that X belongs to A. Now, what if X belongs to this intersection? Okay, let's analyze this case, analyze this scenario. When X belongs to the intersection of BI's, what's the meaning of that? It means that by definition, X belongs to each one of these BI's. So X belongs to B1, and X belongs to B2, and X belongs to B3, and so on. Okay, so X belongs to B1. Well, since X belongs to B1, by definition of union, X belongs to A union B1. X belongs to A union B2, and so on. So what's the meaning of that? It means that X belongs to the intersection of these sets, am I right? A union B1, intersection, A union B2, intersection, the rest of them. So X belongs to the intersection of A union BI. I start from 1, goes to N. So in either case, we show that X lands in the intersection of A union BI's. So we're done with 1. How do we prove 2? So let's see, should I erase the board? Okay, let me erase the board. I need a little bit of more space here. So we're done with A, with 1. Now we're going to show 2. To prove 2, we take an element in the intersection. X belongs to the intersection of A union BI's. I start from 1 to N, and we show that that element lands in A union intersection of BI's. I start from 1 and goes to N, stop at N. Let me make my union a little bit more prettier. Perfect. So X belongs to the intersection of the unions, all right? So what's the meaning of that? It means that X belongs to the first and second and third and so on. So X belongs to A union B1, and X belongs to A union B2, and the rest of it is just definition, right? So when X belongs to the union, it means that X belongs to the first set, or it belongs to the second set, or in both of them. So if X belongs to set A, then remember that by the definition of the union, then by definition of union, X belongs to a union with any other set. Any other set. That's it. Can be written for the sake of our proof. X belongs to a union with intersection of BI's, i's from 1 to N. So in this case, we're done. However, if X is not in A, if X is not in A, then what do we have here? X is not in A, all right? So X is a member of each of these BIs. Then X belongs to B1 and X belongs to B2 and the rest of them, all right? Because X belongs to each of these sets, not in the first set, so it must be in the second set. So it is a member of the union. So X belongs to the intersection of BIs, I start from 1, goes to N. But again, by using the definition of union, X belongs to this set, union with any other set. Union with any set. For the sake of our proof, we're going to take that set as A. So X belongs to intersection of BIs. I start from 1 to N, union with set A. So in either case, we show that X from the first set lands in the second set. What is the conclusion then? The conclusion is that since these two sets are subsets of each other, so they must be equal. Conclusion. Since these two sets are subsets of one another, they must be equal. There is no other choice, and we're done with our proof here.